Hi folks, welcome to part 2 of the second optimization lesson. So again, hopefully you've given this problem a try, at least try to draw a diagram. So let's see what's going on. Is we have a boat that leaves a dock and heads west at a given speed, and at the same time another boat heads north at a given speed and reaches the same dock at 1 p.m. And we want to determine when the boats are closest to each other. Okay, so since we're looking for when they're closest, clearly we're going to have to find some equation for the distance between these two boats. All right, so again, I'm pretty sure we're going to need a diagram here to figure out how to do that. All right, so I want to figure out where to place my dock. So let's see what's happening. I know that one boat leaves the dock and heads west, so it has to go in that direction. So I'm going to leave myself some room to the left of the dock. And the other boat, notice, doesn't leave from the dock, but is heading towards the dock. And since it's moving north, it must have started south of the dock and is moving northward. So I'm going to draw my dock here. I'll use this dot here. Okay, since I have to go west and I have to head north towards that dock. All right, so let's draw the first boat. So the first boat actually leaves from the dock and travels a certain distance towards the west. Okay, let's say I call that distance x. Okay, now the other boat starts somewhere south of the dock and heads north towards it. So it's going to travel a certain distance north towards the dock. I'll call that y. And we want to determine when the boats are closest together. So at some point, they're going to be closest together. Okay, wherever that is, and I'll call that distance d. All right. So, question is how do I determine a relationship for this distance here? Not too obvious. Okay, but this is where we want to look at this diagram and see if we can find something familiar. And what hopefully you're seeing is you're seeing a right angle triangle. However, the right angle triangle is not made up of the two distances that they travel. Okay, because this side length here is made up of the distance traveled by the first boat, but this second distance in my triangle, okay, is not the distance traveled by the boat itself. So we're going to have to find a way to hopefully use this value y to come up with a formula for that side length. Because if I do find a formula for this side length, then I can connect these three things using Pythagoras. Okay, well, let's take a look here. We know that the second boat heads towards this dock, and it takes exactly 1 hour because it says that it leaves at the same time, meaning at noon, okay, and reaches this dock at 1 p.m. So that means it travels for 1 hour to get from its starting point to the dock, okay, and since it's traveling at 20 kilometers an hour, we can figure out that this total distance must be 20, okay, which means that this distance here is 20 minus y. All right, and now I have a relationship between the distance between the two boats, okay, and the distances which either they traveled or is related to the distance that they traveled. Okay, so let's write that down. We have our formula that d is equal to, since it's Pythagoras, just the square root of the square, sum of the squares of both sides, so x squared plus 20 minus y squared. All right, so we have a model with which to work, and yet again we have that familiar scenario where we've got two variables in my equation. Okay, so I'm going to have to find a way to write this in terms of one variable. Okay, now notice here that we've used distances, which makes sense because I'm looking for the smallest distance between them. So I need to create a right angle triangle with distances, but the information that's given is in terms of speeds. Okay, now we're going to make an assumption here, which is an assumption we often make in these simpler math problems, is we're going to assume that this speed is constant. Okay, so remember that we have a relationship with constant speed, that the speed, okay, or velocity, is just given by the distance over the time. So if I want to look for a relationship for the distance is just speed times time. So in other words, x is just, well, its speed is 25, so 25 times the time that is traveled, okay? And then y is just going to be equal to 20 kilometers per hour times the time that's been traveled. And look what I've done. I've now managed to write these two variables in terms of the same variable. Okay, similar to what we did in the first problem in this lesson. I was able to take the unknowns that I had in my equation and write them in terms of a third unknown. Okay, because these boats, okay, remember, leave at the same time. They both leave at noon, so they're traveling for the same amount of time. Hence, it's the same time variable for both of these distances. So that means I can now rewrite my equation as the square root of 25t squared plus 20 minus 25t all squared. And look what we have. We now have an equation for the distance between the two boats, okay, with respect to that one variable time. Okay, so we've accomplished what we needed to accomplish. Now let's see if we can figure out what the domain of this model is going to be. Okay, well here they both leave at noon, and I think it makes sense to end this experiment at 1 p.m. because once the second boat reaches the dock, well, clearly the distance between them is just getting larger and larger and larger. Okay, so definitely past 1 p.m., there's no way that they can be at their closest. So it makes sense that, and what I'm going to do is I'm going to, instead of using 12 and 1, or 12 and 13, if we're talking about military time, if you know what I'm talking about, I'm going to let t be the time from 12 noon. So I'm going to let t has to be greater than or equal to 0. Okay, so that would represent noon, and less than or equal to 1, and that would represent 1 p.m. So here I'm just going to specify that t is time from noon. All right. And what's nice about this is that it's a closed interval, which means I'm guaranteed an absolute max and an absolute min, since this is definitely a continuous function between 0 and 1. All right. So now that we have our model with our domain, let's now go ahead and do the calculus. Now, you might be wondering, why am I not expanding this? And this is because that's going to be an annoying procedure to expand this and then simplify, whereas I know that when I'm taking the derivative, I can just use the chain rule instead. Okay, so again, I'm going to make use of my chain rule so I can avoid doing a bunch of annoying algebra. Okay, so before I go on, let me just recap how I found this model. Okay, so I had my dock. I had one boat that was leaving from the dock, so I could represent its distance with this arrow moving westward. Okay, whereas the second boat was heading toward the dock in the northward direction. So I represented the distance it traveled by this arrow here. And then at some point in time between 12 and 1, they would be at their closest. Okay, so that was represented by this line here, which I then realized allowed me to create a right-angled triangle. But the trick was that only one side was given by the distance traveled by the boat. I had to interpret an equation for that other side. And it turned out to be the total distance of 20 that boat 2 travels from 12 to 1. Okay, and then I just subtracted that total by what the boat actually traveled. Okay, this 20 minus y. Then from there, in assuming that the speed was constant, we were able to write both x and y in terms of the speeds that were given as 25t and 20t. All right, so let's now do the calculus portion. So I have to take the derivative of this here. So again, I'm going to use d prime, but the assumption is that I'm taking the derivative with respect to whatever variable it's given in. So this is the derivative with respect to time. Okay, so this whole thing inside is my u. So the derivative of square root of u is just 1/2 times u. So 25t squared plus 20 minus 25. Sorry, this should have been, hopefully you noticed that mistake. This should have been 20t. Okay, 20t. See, good thing I noticed that. That would have caused some issues. Okay, squared to the negative 1/2. Okay, now times the derivative of this inside function. And this is where, like I said, I'm going to use the chain rule to help save me from doing all that algebra. So the derivative of 25t squared, well, now this here becomes my u, so it's going to be 2 times 25t to the 1 times the derivative of 25t is just 25. Okay, I'm going to try to make sure I have enough room here. Plus, similarly here, this is like my u, the derivative of u squared is 2u, so 2 times 20 minus 20t to the 1 times the derivative of 20 minus 20t, well, that's a constant, so this is just going to be negative 20. All right, now, of course, we want to determine when this thing is equal to 0. Okay, and what's nice here is that all of this stuff is going to go into the denominator. All right, so let's try to simplify this here as much as we can. So I notice I have this common factor of 2, so I'm just going to take it out. Okay, and let's see what we're left with here. We're left with 25 times 25, that's 625t. Okay, remember we're getting rid of this 2 here because we factored it out. Okay, so here we've got negative 20 times 20, so that's negative 400. Okay, and again, negative 20 times negative 20, that's going to be plus 400. Okay, and then here, what do we have in the denominator? We've got 2 times, well, the square root of this thing here, square root of 25t squared plus 20 minus 20t squared. Okay, and hey, these 2's cancel out. Okay, so now, actually, it's kind of nice because this whole thing in the denominator is not going to come into play. So while this looks kind of ugly and complex, in the end, because it's a fraction and I want to determine when the fraction is equal to 0, I just have to work with the numerator. All right, so I just have to determine when the numerator is equal to 0. So here, what do we have? 625 plus 400, that's going to be 1025t minus 400. So let's solve for t. T is going to be equal to 400 over 1025. So let's get an approximation for that. Now, because this is an application question, it's assumed that we're looking for an approximate answer. So here t is going to be 400 divided by 1025, which is about 0.39. And in fact, this is our only critical point. Okay, but because, remember, we're working on a closed interval, all I have to do now is test the distance at the critical point and test the distance at the 2 endpoints, and whichever is smallest is going to be our absolute minimum. All right, so let's start with d at 0. Okay, let's see what we have. So I'll work with this equation here. So that's just going to be 0. So this is going to be 0. So I just have the square root of 20 squared. That's just going to be equal to 20. Okay, nice and easy. Let's now take a look at d at 1, the other endpoint. Okay, so again, d at 1, so that's when t is equal to 1, I just have 20 minus 20, 0 squared, so that's 0. So I'm just going to be left with the square root of 25 squared, which is just going to be 25. Okay, so far, this is the shortest distance. And now let's put in d at 0.39. All right, so let's use our calculator for that one there. Okay, so let's see what we have. So I'll save the square root for the end. So we've got 25 times 0.39, okay, and squared, okay, and then plus, let's put that all in brackets, so 20 minus 20 times 0.39 all squared, okay, and then we're going to take the square root of that, so exponent 1/2, and looks like we have 15.6. which is clearly the shortest distance. All right. So let's now go back and see what they're actually asking us for. Okay, so they're not asking for the shortest distance. They're asking us to determine when the boats are closest to each other. Okay, well, let's recall what 0.39 represents. It represents a time value from noon. So that means it's 0.39 of an hour past noon. Okay, but here I want to be a little more precise here. So what is 0.39 of an hour? So let's just calculate 0.39 times 60. Okay, so we can at least put it into minutes. All right, and that's equal to, okay, 0.39 times 60 represents about 23.4 minutes. Okay. Okay, so that means our answer, okay, at approximately 12:23 p.m. Okay, because about 23 minutes past noon. Okay, so again, let's recap. We already did a recap of how we found our model with our domain. Okay, definitely important to get a diagram with that. Okay, we noticed that while we weren't working with the nicest of functions, because we just want to determine where it's equal to 0, we just had to work with the when the numerator was equal to 0. And because we were working on a closed interval, I was able to determine my absolute minimum by just determining the distance at the two endpoints and at the one critical point that we found. And we saw that the minimum occurred at the critical point. And in order to write it as a more appropriate time value, since this is given in terms of a fraction of an hour, I just multiplied by 60 to convert that into minutes, and I was able to determine the time at which they were at a shortest distance. You know, if the question had been what was the shortest distance between them, well, that would have been 15.6 kilometers. All right, that's it for this one.